Hi, let's come back to our systolic architecture right where we left it. Before starting synthesizing the kernel, how do we specify to Vivado HLS that we want to each element of the diagonal 4 to be executed in parallel? We could, for example, specify to completely unroll the loop. However, if we directly place a pipeline pragma on the external 4, Vivado HLS will pipeline the external loop and unroll all the loops that are below this inner loop. Let's also reduce the size of the problem to 32 × 64 so that the synthesizer works faster, and let's specify a different port for the direction metric _G port. The first feedback provided by our log is the one in blue in the console. As you can observe, Vivado HLS is telling us that it is ignoring the pipeline pragma of a subloop, as its parent is already pipelined, and then is unrolling all the loops below the one we have pipelined. Here we go. We have synthesized the kernel. Firstly, notice that not all the loops are represented here, as most of them have been completely unrolled. Unfortunately, the initiation interval of the num_diag4 is equal to 32. That, by the way, is the size of the query we have specified. Dipping more into the log, we can firstly notice that the estimated clock cycle is greater than the 5 nanoseconds specified by SDXL framework. However, this is not a final value, as once we will implement the kernel, the value may be different. If we think a little more about what are we trying to implement here, we can notice that we have three buffers: the dependency one, the query, database, and direction diagonal that needs to be read and written simultaneously in the same clock cycle. However, it is not possible to perform such an operation if we are using BRAM on our FPGA. The most straightforward thing we can do is try to implement these buffers using the logic of our chip. Departitioning partitions an array into smaller arrays or individual elements, resulting in having multiple registers or multiple smaller memories. In this way, we are increasing the amount of parallel read and write while increasing the amount of area used on the FPGA. To specify to Vivado HLS that we want to partition some of the buffers in our code, we need to click on the Directive tab in the right part of the screen, right-click on the desired buffers, insert Directives, and let's select Source File so that we can read all the optimizations we are writing, and then select Array Partitioning and confirm with OK. As you can see, we have now the pragmas in our kernel, and we can try to synthesize again our kernel. Now, let's first notice that we are able to infer burst for both the reads and our write. However, there is still something wrong. We can understand it from two things. The first one regards the burst write. It is in fact inferred just for 32 elements, the size of an anti-diagonal, while we are performing this write for each anti-diagonal. This number should be way larger, in particular n-1 plus 1 times n. This thing is confirmed from the warnings we have while the synthesizer is trying to pipeline function store diagonal. In fact, it is telling us that it is unable to store completely one anti-diagonal per clock cycle, delaying the store of all the successive anti-diagonals. We can address these issues by implementing a data compression on the direction matrix. The compression is doable as we have four possible directions that we have to store: north, northwest, west, and center. We can express these four possibilities using just 2 bits without any loss of information. In order to do so, Vivado HLS provides a data structure called APUint. To use this data structure, we just need to include its library and then select how many bits to use. In this example, we will use 512 bits elements, as it is the maximum size of a port from the kernel to the DDR memory, and allow us to send up to 256 elements each clock cycle. Now, we need also to change the buffer for the direction diagonal. Let's call it compress diagonal, and let's change all the functions to use this new structure. The APU in data structure comes with a range function that allows us to read or write specific bits inside the variable. We hence need two variables, to and from, to keep track of what bits we need to set, and to change the way we store the directions using this range function. We need then to update the two indexes, to and from, for the next iterations. Update the store diagonal function to reflect the new data structure we are using, and finally, change the way we are updating the directions index, so that it increments every time by 1. Note that by doing this, we are fixing the size of the query to a maximum of 256 elements. Furthermore, we are always moving, each clock cycle, 512 bits from the kernel to the DDR, even if we have a smaller query. This is not a huge problem, as we are able to do this in one clock cycle. However, it is a waste of memory bandwidth, as we are moving more data than needed. Wait, there is another thing that we forgot to mention. In the previous lessons, we have said that in order to reduce the amount of logic to remove corner cases, we would have buffered out corners. In practice, this means that we are computing always the same amount of data, even when the anti-diagonal is composed only of one element. In order to allow this kind of computation, we need to increase the size of our database from m to m plus 2 times n minus 1, so that we are covering corner cases too. These pictures you see now is the same I showed you in the previous lessons. However, in this image we added n-1 characters in the database both at the beginning and end of the string to handle corner cases. Okay, let's now define a database size, and let's put it equal to m plus 2 times n minus 1. Then, let's change the buffer size in our kernel code. As we define the different functions in our kernel, if we want them to be inlined, in upwards, and recursively, we can specify this behavior using this particular function in our inner function. Awesome! We have our first Systolic array architecture, and we achieve the II of 1 on all the loops in our code. Now that we have specified the architecture, we need to adapt the host code to test if the code we have written is correct. I already adapted my host file so that it's capable of ordering the output direction matrix and comparing it to a correct version. Therefore, let's compile and start the execution to check the results. Great, the results are correct. Now we just need to build the system and check on our target architecture what kind of performance we can achieve. While the system builds our FPGA implementation, let's see how the operational intensity changes in our code. I will not show you again how to perform the stated code analysis. However, the code presented here achieves an operational intensity equal to 15.4 in the worst and 13.49 in the best case when the query size is equal to 32 and the database sequence is 64. Increasing the size of the query to 64 and the database to 128, we obtain 30.7 in the worst and 26.7 in the best case. Finally, if we try to implement the architecture with a query size of 256, we obtain an operational intensity of 122.24 in the worst case and of 106.48 in the best case. This improvement in operational intensity is mainly caused by an increase of operations performed by our architecture and a decrease of memory traffic, especially because we avoid sending back the similarity matrix and we are compressing the direction one. Notice that we are always sending a 64-byte variable each clock cycle, hence the dimension of the output at each clock cycle is the same even if you use a query smaller than 256 characters. Checking the performance on our roofline, we see as we are still in the memory bound area for all this operational intensity, although with a bigger dataset we are close to the reach point. Considering expected performance, with our first dataset we expect performance in the order of 128 giga operations, while with the second one we expect almost 2 times this value. And finally, with a dataset where the query size is equal to 256, we expect performance in the order of 1024 giga operations. As of now, I launched 2 builds for my Vertex 7 FPGA, with query size equal to 32 and 64, and the database to 64 and 128. Now, let's see how they execute on my Vertex 7 FPGA. Okay, let's start with the first one. Awesome, results correct and execution time equal to 0.1393 milliseconds, resulting in a performance value equal to 0.68 giga operations. Let's now check our second dataset. Again, results correct, and now the execution time is 0.14 milliseconds. This is awesome. We have almost the same execution time, but we have a way bigger dataset. In fact, our performance now are equal to 2.68 giga operations. For both the tests we have performed so far, we are way far from the performance predicted by our roofline model, but there is room for more optimization. The first thing we could do is increasing the dataset of our accelerator, as the FPGA works very good when managing a huge amount of data in a data flow manner. Furthermore, the best performance on the FPGA are achieved once we are increasing the query size. This is because the size of the query determines the number of parallel processing elements on our FPGA device. So, let's increase the size of the dataset and let's see what kind of performance we can obtain. But first, let's try to synthesize the kernel using Vivado HLS. Unfortunately, the kernel code with this specific dataset does not fit entirely on our FPGA device. It would require, in fact, 130% of the flip-flops and more than 180% of the available LUTs. In the following lessons, we will see how we can change our code so that we are able to manage bigger queries, resulting in increasing the level of parallelization on our chip.